Okay, we learned in the last movie that every circle, the distance around is somewhere around 3 times the distance across. In other words, the ratio of the circumference, that's the distance around, over the diameter, is a number between 3 and 4. We only narrowed it down to 1 digit. You could get it more accurately by actually measuring, but then you're limited to the accuracy of your measuring tools. What if we want to have a lot more precision? Somebody in around 200 BC, Archimedes, came up with a method of finding pi as accurately as you care to do. And the way he did it was he started with a polygon inside a circle. And he started with a hexagon, so that's what we have here, a 6-sided figure. And a hexagon is exactly 6 times as far around as the radius, because these are equilateral triangles. And so if the radius here, let's just bring that in here, if the radius is 1, and then the side is going to be 1, and so the distance around is 6. The diameter is 2, and if you take the ratio of the circumference, and in this case the perimeter, over the diameter, it would be 6 over 2, which would be 3. So that's how we come up with a first approximation. But we'd get a better approximation if we came up with a polygon with more sides. If we can figure out a way to extend what we know about a hexagon to, say, double the number of sides, that would be a lot closer. And if we could do it again, we get a lot closer still, and do it over and over, and that's how we can approximate pi as accurately as we want. So the question is, if we know the length of a side of a 6-sided figure, how can we find the length of a side of a 12-sided figure? So if we split each of these in half, we'd have twice as many sides. That would be 12 sides. Okay? So let's do that. Let's take this side here, and let's find the midpoint. Okay, and let's draw a ray from the center to here, there, and see where it crosses the circle is halfway along this arc. So now let's do a polygon that goes from here to here, and let's say that this time we're going to have 12 sides to it. Now we have a 12-sided figure. Okay. Now, the question is, if I know the length of the side for the hexagon, how can I find this side? It turns out all it takes is the Pythagorean theorem. You know, if you know 2 sides of a right triangle, you can always find the 3rd side. So let's look at this carefully. This length here, we said, is 1. Now this length is also 1, but I'm going to label it just S. I'm going to label it just S1 here for the length of the side, because I'm going to apply this same method when we're not using a hexagon. When we're using a 12-sided figure, we want to find the length of a side for a 24-sided figure, and so forth. So whatever the length of this side is, the length of this distance right here, from the midpoint down to here, is half of that. So it's S1 over 2. Okay. Well, notice we now have 2 sides of a right triangle. And so I can find this side. Let's just label that side A. And I can come up with that by the Pythagorean theorem. Notice we know that the hypotenuse is 1. And so if I take that side squared minus this side squared, that'll give us this side squared. So A is the square root of 1, or 1 squared, however you like. 1 squared is 1, minus S1 over 2, and it was half of the side squared. All right? And then you take the square root of the answer, and that gives you A. All right? Next, let's find this little length in here. Now, that's the distance here from J to K. Okay? How do you find that? Well, we know that the radius of the circle is 1. And so if you know that the distance out this far is A, you can take 1 minus A, that should give you B. So that's our second formula. B is 1 minus A. All right? Now look what we have. We now have another little triangle in here. This right triangle, we know two sides. We know this leg and this leg. And so I can find this side here. We can call that length S2. So this is the side of our starting polygon, then this is the side of our ending polygon. And notice that S2 is given by the Pythagorean theorem again. S2 is this length squared, that's b squared, plus this length squared, that's 1/2 of our original side squared. And then you take the square root. Okay? So, it's a simple three-step process. We know the side of a six-sided figure, and so using the Pythagorean theorem once, we find A, subtract it from the radius, which was 1, and you get B, and then use the Pythagorean theorem for this little triangle, and you get our final one. Now that may seem tedious. First of all, notice that Archimedes did this by hand, and he did this by going over and over again, starting with 6 to 12 to 24 to 48 to 96. He did it as far as a 96-sided figure by hand. Now he didn't use exactly this method. He used a method that was somewhat more complicated, but it was the same basic idea, starting with a 6-sided figure and doubling it repeatedly. We have an advantage that we have better math notation to work with. We have better tools to work with. So let's pull up a spreadsheet and see how we can use that to do this computation. Okay, I'm using here an OpenOffice spreadsheet. You can use Excel if you have Microsoft Office available, or some other spreadsheet. I've already started it just to save some of the labor here. I've labeled my columns, and so n is going to be the number of sides in our polygon. So let's start with n equals 6. So I'll put a 6 there. Length of the side for a 6-sided figure is 1, because we said it was an equilateral triangle. So the side length is the same as the radius. All right. This length is half of that. I could just type in a half, but I don't want to do that. I'm going to put in a formula. So I put in an equals, then I point at this and I say that divided by 2. Why am I doing that? Because if I'm using a formula, I can say whatever this happens to be, and it's not always going to be 1. As I go down to greater polygons, it's going to be other numbers. So here we have the length of the side. Here we have half the side. Let's bring up our diagram again and remember how we get A. Okay, A we see is the square root of 1 minus S1 over 2, the quantity squared. In other words, just think of this diagram here. This side, which is half of the side length, and then the 1, I'm going to square them both. I'm going to subtract and take the square root, and that should give us A. Okay, so I'm going to say equals. That's the way it indicates it's going to be a formula. SQRT. That tells us that we're going to do a square root here. Okay, and we're going to go inside that. Let's see, go right here. I could do it up here at the top, but I'll do it in here. The square root, and that's going to be 1 minus S over 2, that's this number, squared. Okay? And that's our answer is 0.87. How do we find B? Let's go back and remind ourselves. B is simply 1 minus A. Remember the picture. B is the little gap here between this point and the circle. And so the radius of the circle is 1. This part is A, so I subtract to find B. Okay, so this says equals 1 minus that. Okay. Next, I want to find the new side for this time it'll be for the 12-sided figure. Let's go back and look at it. So that's going to be looking for this side right here, S2. And notice that I can use the little triangle. So the B and the previous side over 2. I'm going to square them, add them together, and take the square root. Okay, so I'm going to say equals. I'm going to take this number squared plus this number squared. I notice that I forgot to take the square root. I square them, I add them together, I want to take the square root of the result. So I put SQRT in here, and I'm going to have to, I'll go up here and do it. I'll put the parentheses to close it out. What happened? There. Okay. Now, by the way, I can get better precision on all of these. Even though it only showed a few digits, internally it was using all of the precision the whole time. Once I have the new side, I can go ahead and calculate the next one. But before I do that, let's stick with this six-sided figure for a minute. What was the perimeter? The perimeter of this is equal to the number of sides times the length of the side, which was 6. Now, since the diameter of the circle is 2 in all of these cases, I can simply say this is equal to this divided by 2, which is 3. That's our estimate of pi, remember, for the six-sided figure. Let's go to the next row. What I'm going to do now is double the number of sides. So instead of typing 12, what I'm going to do is put a formula that says equals the previous number of sides doubled, so times 2. There we go. What about the length of the side? Well, this is simply equal to the length of the side we computed a minute ago. So it's equal to this, which is column F and row 2. That's why it says F2. And notice that the rest of these are already formulas. Notice up here, each one of these is a formula, not a constant. So watch this. I'm going to use the same formula, but with different values now. Pull that down, and here's what I've got. I now have this S is 0.51. The new S divided by 2 is half of this. The new A is by evaluating the same square root thing. Except previously, notice, look at this. The first row here for the six-sided figure, it said 1 minus C2 squared. Well, C2 is column C, row 2, which is the 0.5. Look what it says here. This says 1 minus C3 squared. Well, C3 is row 3. So by pulling the formula down, it's going to use the value that's on the same row here. Okay, now let's take all of these. Since all of these are now formulas, let's just pull it down a ways and see what we have. Whoops, this one's a little bit not big enough to hold the number. In fact, I don't need this number to have a lot of decimal digits because they're all zeros. So that's going to be a whole number. Let's just shrink that back a bit. And here we go. Remember we said Archimedes went as far as a 96-sided figure? And notice that that gives us a value of pi that's approximately 3.141 something. Okay, about 3.14. As I keep on going, notice that more and more digits look like they stay constant, and it's only changing further and further out here. And so by going further out, we can see that we're getting closer and closer to what we might recognize as pi. Let's make this column bigger so we can hold more digits. Okay, let's do this. So for this column, I'm going to add as many digits as I can get away with here. Now notice the last digit's 0 on all of these. We've gotten to the maximum size of the number, so let's back off one. That's the maximum size number that this can handle. And these numbers down here are accurate to 3.1415926, and then they start varying. Okay? Well, let's go further. Let's see how far we have to go until these numbers start being the same every time. Coming on down here, notice they keep changing until we get 966, 976, 979, and from there on, it stays the same. Okay, so let's delete everything from this point on because we're not making any further progress. And let's see what we have here. Okay, we have an estimate of the value of pi by taking a, what's this, 25,165,824 sided polygon, And by finding the ratio of the perimeter over the diameter, right there, we're coming up with 3.1415926535897 and if we had a bigger base for numbers in this program, we could calculate it farther. But we've gone as far as our spreadsheet program is able to handle the numbers. Okay. By the way, the spreadsheet itself has a value of pi embedded. Let's compare this. If you have a calculator that has a key for pi, a scientific calculator typically has that, you can look at it there as well. So to find the pi function, you put an equals, type in pi, and notice that it right here it says you have some parentheses. So if you're going to have a function in this programming language, you need to include a pair of parentheses, even though nothing's in them. Okay, and there you go. Notice that the value of pi stored in the spreadsheet program is identical with the one that we've computed. So, in the first program, using nothing more than a square and a hexagon, we found that the value of pi had to be something between 3 and 4. This time, we've extended ourselves further, and we've found a way to go from a 6-sided figure, doubling it every time, to 12, 24, 48, etc., and compute the value of the perimeter over the diameter in each case, and this gets closer and closer to the distance around a circle compared to its diameter, which is the definition of pi.